Hello everyone, and welcome to this session, Impact of Defects and Measuring Defect Levels. The learning objectives are to be able to discuss the impact of defects in a process, calculate process yield and parts per million, ppm, to discuss the importance of a low fraction defective per part for complex products, and to understand the difference between a defect and a defective part. This will also help us to understand the terms defect per unit, or DPU, and defect per million opportunities, or DPMO, and we'll look then at how DPMO differs from ppm. And finally, we want to discuss the importance of preventing defects. But first, what do we mean by the word defect? And so in this course, we're going to say that a defect occurs during any process when the outcome of the process is not our expected outcome. And what we mean by that is that the expected outcome is the outcome that we have specified in advance. It's what we want the process to produce. And if a defect occurs, then the outcome of the process will not be as we expected. In other words, a defect is a flaw or an error or a discrepancy. And just to put this into a little more visual context, here are some defects from my former work. Here we have some random defects, some particles that deposited on the semiconductor wafer. These could potentially cause the integrated circuit, the chip, not to work. Here we have also, same thing, silicon wafers with, here's some systematic defects. Here we have gouges, for example, in the film, or lines that are not printed correctly. They're also unwanted. They're not part of the specified outcome of the process, and then could cause a defective part. Now let's look together at a simple process for making crayons. The two basic ingredients for crayons are paraffin wax and pigment color. These are then mixed and stored in heated gallon tanks, which I didn't actually put here. And then they're heated, this is a storage facility, they're heated up very, very hot and melted, and then poured into a mold of crayon-shaped holes. And a single mold can make over 1,000 crayons at a time, for example. You then cool the mold, and then an operator will use hydraulic pressure to eject the crayons from the mold. And then they're labeled and packaged. And so a crayon manufacturer, a big one, could produce 2 to 6 million crayons in a day, for example. Now, why worry about a few defects? You're the manager of a crayon manufacturer. Out of 100 batches of paraffin wax and color pigment used for the crayons, an average of 1 batch does not match design specifications. When you find out about a bad batch, you need to scrap around 40 batches. But you estimate that the scrap costs are very low. In fact, the scrap costs for this 40 batches is less than 0.05% of the cost of goods sold, extremely small. So you say the problem is under control. Now, from a quality perspective, are there any flaws in your thinking? Let's look at this together. So here we see our crayon flow again. Now, a defect is produced somewhere in our process. Let's just arbitrarily draw defect occurs. And this leads to, in my example, to a defective crayon. Let's see, defective crayon. Defective product, or if we were a service process, it'd be a defective service. Where are our costs here? Now, before the defect occurs, and we just did this in the face-to-face class with the students, And they said correctly, before the defect occurs, you have costs due to the materials. Now we said that's not so much in this example. Even when we scrap the batches, we know that it's a small amount of money. But where else do we have costs? Well, we have also the labor that went into making that crayon. So the people that we've hired for our process, they're there to make the products, and we're paying them for making parts that we cannot sell. Now, the other interesting thing is if we have a process where we have a high demand and we have a capacity constrained process, then we're using, well, in both cases, even if it's not capacity constrained, we're using up capacity on machines. We're using up the energy costs, for example, for heating up those the mixture. The molding machine, we're molding products that could potentially not sell. So the capacity is being used up. And this can be critical when we have a capacity constrained process, which means we need every single part of our capacity, every minute of our capacity we need to make good parts to meet the demand. So these, though, in this part of the factory, we've got internal failure costs. Which, although they may be small, they're very real. Now, the other problem is that we have this defective crayon. I really didn't write that right, did I? Crayon. And this defective crayon might end up getting out to the customer. Now, in the case of crayons, maybe it's not that critical. It depends if there's something toxic in it or something, then it'd be critical. But you can think of this applied to to another product, like a car or like some kind of medicine. If that defective product gets out to the customer, we have, for example, warranty costs, liability costs. We could have, even worse, recall costs. We could, even worse, have the loss of reputation. And loss of reputation leads to things like lower prices. We're forced to sell our product at a lower price, or even loss of market. The demand will drop. And these are called then the external failure costs. And these external failure costs are often underestimated. So even if you're arguing that the scrap of the material is not that much, there's other things you need to think about. And one of the most important ones is what happens if that defective part gets out to the market. And there's one more thing here. Can you think of one more thing, one more problem? It's the idea that if you allow one batch of 100, so one batch of 100, you're looking at 1% of poor material. If you allow that, you are creating a culture, 1% defective are okay. And what we're going to see very soon is that even if small percentage of defectives can accumulate to very, very substantial failure rates for an entire process. And these are crayons. We just have a few parts. What if you have a very complex process? For example, as we said before, like a car.